In the last video, we learned how to use Newman projections to depict different conformations of molecules. In this video, we'll talk about the relative energies of some of the different conformations. In the last video, we saw staggered and eclipsed conformations of ethane. Which of these two conformations do you think would be more stable or lower in energy? You should predict that the staggered conformation is lower in energy or more stable than the eclipsed conformation, which is higher in energy or less stable. And that's because in this eclipsed conformation, the hydrogen atoms that are eclipsing are very close to one another. And this interaction is unfavorable, and it has an energetic cost associated with it. And more specifically, that cost is 4 kilojoules per mole, or 1 kcal per mole, for each hydrogen-hydrogen eclipsing interaction. Those energies are additive, so the staggered conformation of ethane is 12 kilojoules per mole lower in energy, or more stable than the eclipsed conformation. This type of energy cost is referred to as torsional strain. Let's pause for a quick concept check question. Take a minute to draw both the staggered and eclipsed conformations of propane. I'll always start by drawing out the structure using dashes and wedges. So here I'll do that first. I'm going to look down the carbon-1, carbon-2 bond. So I'll draw the carbon-1, carbon-2 bond horizontally. Okay, now if we're looking down the carbon-1, carbon-2 bond, that will put our methyl group in the back. If you look down the carbon-2, carbon-3 bond, and you want to compare your Newman projection to mine, you might want to pause the video and draw the other form. Okay, so we're going to look down carbon-1 to carbon-2, and that's going to put the methyl group in the back, pointing up. So this is carbon-1, carbon-2, and carbon-3. When I draw a Newman projection, I always start with the back carbon. I find this to be the most straightforward. So on the back carbon, as we noted, we have a methyl group pointing straight up, 2 hydrogens pointing down, 1 to the left and 1 to the right. And then our front carbon has only 3 hydrogens on it. And I've chosen to draw the staggered conformation first. Now to draw the eclipsed conformation, I can simply rotate the front carbon by 60 degrees. I keep the back carbon stationary. I only rotate the front carbon. And now I have an eclipsed conformation. Okay, again, the back carbon stays the same. I rotate the front carbon. And so I can draw the back carbon the same as I drew in the staggered conformation. And then on the front carbon, I have 3 hydrogens. And each hydrogen is in front of a group on the back carbon. They're eclipsing the groups on the back carbon. And now in this eclipsed conformation of propane, we see we have the hydrogen-hydrogen eclipsing interaction that we've already seen. But we also have a new eclipsing interaction of a hydrogen and a methyl group that we haven't yet seen. And this eclipsing interaction has a higher energy cost than a hydrogen-hydrogen interaction because the methyl group is larger and it creates greater torsional strain. So this hydrogen-methyl eclipsing interaction costs 6 kilojoules per mole. Okay, so far we've looked at the conformations of ethane and propane, and in both cases we have only one staggered and one eclipsed conformation. But for larger molecules, more conformations exist. And we'll see this by looking at butane. I'm going to start, as I always do, by drawing my dashed wedged depiction of butane. So I'll take butane, and I'll make sure all 4 carbons are in the plane of the paper, or the plane of the screen. And I'm going to look down the C2, C3 bond. And I'm going to draw that bond horizontally. I'll orient the model so that we're looking down that C2, C3 bond. And what you see is that on the back carbon, there's a methyl group pointing straight up. And on the front carbon, there's a methyl group pointing straight down. So this is the staggered conformation of butane. And in this particular staggered conformation, the two methyl groups are pointing 180 degrees from one another. Okay, now we can explore other conformations of butane. We can rotate the front carbon by 60 degrees, and we arrive at an eclipsed conformation. And as we continue to rotate the front carbon, we approach another staggered conformation, where now the two methyl groups are 60 degrees from one another. And this particular staggered conformation, where the methyl groups are 60 degrees from one another, is called a gauche conformation. And then we continue to rotate, and we have another eclipsed conformation, where now the two methyl groups are eclipsing one another. And as we rotate through, we end up at another gauche structure, and then another eclipsed structure, identical to what we've already seen. Okay. Now, as we looked at those different conformations of butane, we saw some new interactions. And as you might imagine, each of these new interactions has a specific energy associated with it. Okay. This methyl hydrogen interaction we've already seen, but a new interaction that we haven't yet seen is this gauche interaction. Okay, and this gauche interaction of two methyl groups, when the two methyl groups are 60 degrees apart, has an energy cost of 3.8 kilojoules per mole. Okay. As we rotate back through and we have the eclipsing interaction of two methyl groups, this has a very high energy cost, and it costs 11 kilojoules per mole. Okay. And we can use those values of the independent interaction energies to compare the overall energies of the different conformers of butane. Right? If we add those torsional energies up, we find that what our intuition might have told us, that the anti-conformation, where the two methyl groups are 180 degrees apart, is the most stable conformation, or the lowest in energy. And now we'll look at the other conformations relative to the anti-conformation. We've assigned the anti-conformation as having an energy of 0 kilojoules per mole. The conformation with the two eclipsing methyl groups is the least stable, or the highest in energy. And then the other gauche and eclipsed conformations are higher in energy or less stable than the anti-conformation. So what we can draw here now is the energy coordinate, or the energy diagram, that corresponds to the changes in energy as we rotate around that carbon-carbon bond of butane. So we fill in the points that correspond to those energies, and then we can map the full energy diagram here. And what you see again is that we have the lowest energy in the anti-conformation. And as we approach an eclipsed conformation, that energy increases. And then as we move away from the eclipsed conformation, the energy decreases. We reach the gauche conformation, which is sort of an energy well, or an energy minimum. And then as we approach the next eclipsed conformation, the energy begins to increase again, and so on. Now let's take a look at this question that we set up for ourselves at the beginning of this video lecture. Go ahead and pause the video and try it for yourself. Try to draw the Newman projection for the lowest energy conformation of 2-methylhexane looking down the C3-C4 bond. Okay, welcome back. We'll start by drawing the structure of 2-methylhexane. First, we can draw the line drawing. And if this is at all tricky for you, then go back and work through our previous video to remind yourself about naming and drawing line structures from names. Okay, now we need to identify the C3-C4 bond. So we number our carbon chain according to our IUPAC naming system. And so this bond, highlighted in green between carbon 3 and carbon 4, is the bond we'll be looking down. I like to reorient the structure so that the bond I'm looking down is horizontal. It's just less for me to try to convert in my head. Okay, I also like to draw the dashed wedged form of the structure to make it easier for me to see. It's helpful for me to visualize this way which groups are coming out towards me and which are going back away from me. Now I'm ready to draw my Newman projection, and I'll start with the back carbon, which has one alkyl group pointing down and two hydrogens pointing up to the left and to the right. Then I'll draw in the front carbon, which has an isopropyl group pointing up and two hydrogens pointing down, one to the left and one to the right. And now because our two groups, the ethyl and isopropyl groups, are pointing 180 degrees from one another, we've drawn the anti-conformation, which will be the lowest energy conformation of the structure. So this is the Newman projection for the lowest energy conformation of 2-ethylhexane looking down C3, C4 bond.